Hi, welcome to Sunil Maths tutorial. Functional analysis class number 30. In this video, we prove a theorem. Let us see the statement. If capital T is an operator on a normed linear space capital N, then its conjugate T star is an isometric isomorphism defined by T star of f of x is equals to f of T of x is an operator on the conjugate space n star, and the mapping T from to T star is an isometric isomorphism of script b of n into script b of n star, which reverses products and which preserves identity transformation. One of the lengthy theorem, let us prove this one. So in the initial stage they given that let capital T be an operator, capital T be an operator on n, and n star be the conjugate of n star be the conjugate of n. Now we shall prove that, or we shall show that T star is an operator. T star is an operator. To prove that T star is an operator, it is equivalent to prove that it is a continuous linear transformation. So the first side heading, to show that T star is linear. To prove that T star is linear, let us take elements. Let f comma g belongs to n star and alpha comma beta are scalars. Now consider T star of alpha f plus beta g of x is equals to alpha f plus beta g of x, alpha f beta g t of x. This is defined in our statement. See here, T star f of x is equals to f of t of x, So alpha f plus beta g t of x. So it can be written as alpha f into t of x plus beta g into t of x. Again this can be written as alpha f of t of x plus beta g of t of x. Again it can be written as alpha T star of f of x plus beta T star of g of x. So this can be simply written like this: alpha T star of f of x plus beta T star of g of x. So that is what we prove that. Therefore we conclude that T star of alpha f plus beta g is equals to alpha T star of f plus beta T star of g. This condition shows us T star is linear. T star is linear defined on n star. So this is the first condition. Next we prove that T star is continuous. To show that T star is continuous. To prove that T star is continuous, now define that norm T star is equals to supremum of norm T star of f such that norm f less than or equals to 1 by the definition of function, by the definition of norm of a functional, which is equals to supremum of norm t star of f of x such that norm f less than or equals to 1 and norm x also less than or equals to 1. So again, this is equals to supremum of, by the definition of t star here, norm f of tx or t of x such that norm f less than or equals to 1, norm x less than or equals to 1. So which is clearly less than or equals to supremum of norm f, norm t and norm x such that norm f less than or equals to 1, norm x is also less than or equals to 1. This is nothing but norm f is less than or equals to 1, norm x is less than or equals to 1, the whole condition is less than or it becomes norm t. Therefore, we prove that norm t star is less than or equals to norm t. Norm t star is less than or equals to norm t. Since norm t is bounded, norm t is bounded, which implies as norm t star, norm t star is also bounded. Norm t star is also bounded. If norm t star is bounded, then obviously this t star is continuous. This t star is continuous because every bounded linear transformation is continuous. Therefore, we conclude that t star is an operator. T star is an operator defined on n star. That's it. So right now, by applying Hand-Banach theorem here, this is the second part. We are going to prove norm t star is equals to norm t. We are going to prove that norm t star is equals to norm t. So next we show that norm t star is equals to norm t. So right, to prove that we use the Hand-Banach theorem. By applying Hand-Banach theorem, for each non-zero vector, small x in capital N, there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm f naught is equals to 1. This is one of the application of Hand-Banach theorem. For each non-zero vector x in capital N, there exists a functional f naught in n star such that f naught of x naught is equals to norm x naught and norm x naught is equals to 1. Hence, we conclude like this. Therefore, f of t of x is equals to norm t of x. F of t of x is equals to norm t of x. And also, norm f is equals to 1. Let it be equation number 2. Here, norm t star is less than or equals to norm t is equation number 1. So now, again, we are going to write the definition of norm t. Norm t is equals to supremum of norm t of x, such that norm x is equals to 1. Which is equals to supremum of norm f of t of x, such that norm f is also equivalent to 1, norm x is also equivalent to 1. So which is equals to again supremum of norm t star f of x, norm t star of f of x, such that norm f is equals to 1, norm x is equals to 1. So which is less than or equals to supremum of norm t star of f, norm t star of f into norm x, such that norm f less than or equals to 1, norm x is also less than or equals to 1, which is less than or equals to norm t star into norm f into norm x, which is less than or equals to norm t star only, because these two are less than or equals to 1. Hence what we show that here norm t is less than or equals to norm t star. Let it be equation number 3. Now see equation number 1. Now see equation number 1. Norm t star is less than or equals to norm t. Now see equation number 3. Norm t less than or equals to norm t star. From equations 1 and 3, we conclude that norm t is equals to norm t star. Norm t is equals to norm t star. Right. In the next part, we now show that t extends to t star is an isometric isomorphism. Is an isometric isomorphism. That is there is a mapping pi from script b of n into script b of n star given by pi of t is equals to t star is an isometric isomorphism. So our aim is to show that there is a mapping pi that is from script b of n into script b of n star defined by pi of t is equals to t star is an isometric isomorphism. So first we show that t is linear. In this part, first we show that t linear. So first to prove that isometric isomorphism, first we show that this pi is linear, not t, this pi is linear. So right, let us take two operators t1 comma t2. Let t1 comma t2 belongs to script b of n and alpha comma beta belongs to capital R scalars. Pi of alpha t1 plus beta t2, pi of alpha t1 plus beta t2 is equals to alpha t1 plus beta t2 whole star. So this can be written as excuse me. So now we can alpha t1 plus beta t2 whole star of f is equal f whole star of f of x is equals to f into alpha t1 plus beta t2 of x, which is equals to f of alpha t1 of x plus beta t2 of x. Again, this can be written as alpha t1 star of f of x plus beta t2 star f of x. So again alpha t1 plus beta t2 whole star f of x is equals to alpha t1 star f of x plus beta t2 star f of x. So if you that is you conclude this calculation like this: alpha t1 plus beta t2 whole star of f is equals to alpha t1 star of f plus beta t2 star of f. this is nothing but, again, this is nothing but alpha t1 plus beta t2 whole star is equals to alpha t1 star plus beta t2 star. Using this identity, now using this identity here, using this identity here, you can conclude like this: pi of alpha t1 plus beta t2 is equals to alpha t1 plus beta t2 whole star, which is equals to alpha t1 star plus beta t2 star, which is equals to alpha pi of t1 plus beta pi of t2. Therefore, we conclude that pi of alpha t1 plus beta t2 is equals to alpha pi of t1 plus beta pi of t2. This condition shows as pi is linear. This condition shows us pi is a linear transformation. Pi is a linear transformation. Now we show that this pi is 1 to 1. We have to prove that pi is 1 to 1. We prove that this pi is 1 to 1. 1 1 mapping. To prove that pi is 1 1. So to prove that pi is 1 1, let us take two elements. Let us take two elements. Pi of t1, or directly assume that suppose pi of t1 is equals to pi of t2. So this condition implies as t1 star is equals to t2 star. This condition implies as norm t1 star minus t2 star is equals to 0. Implies as norm t1 minus t2 whole star is equals to 0. Implies as norm t1 minus t2 is equals to 0. Implies as t1 minus t2 is equals to 0. Implies as t1 is equals to t2. Implies as t1, I mean, so this is the required condition. Am I right? Yes, required condition. Therefore, pi of t1 is equals to pi of t2 implies as t1 is equals to t2. Pi of t1 is equals to pi of t2 implies t1 is equals to t2. Therefore, we conclude that pi is 1 1. Therefore, we conclude that pi is 1 1. Hence, pi is linear transformation and 1 1. Pi is linear transformation and 1 1. Therefore, pi is an isometric isomorphism. Pi is an isometric isomorphism. That's it. Pi is an isometric isomorphism. So, to complete our proof of the theorem, it is remaining to prove that pi reverses the product. Pi reverses the product. Pi reverses the product. To prove that pi reverses the product, let us consider t1 t2 whole star f of x is equals to f of t1 t2 of x. This is from definition of t star. So this can be written as f of t1 of t2 of x. F of t1 of t2 of x. This is nothing but t1 star of f of t1 star of f into t2 star sorry, t1 star f into t2 star f. T2 star f. This is nothing but t2 star t1 star of f of x. This is nothing but so we prove the condition t1 t2 whole star f of x is equals to t2 star t1 star of f of x. Therefore t1 t2 whole star is equals to t2 star into t1 star, t2 star into t1 star. Now the original one, pi of t1 t2 is equals to t1 t2 whole star, t1 t2 whole star, it is equals to t2 star into t1 star. This condition shows us pi reverses the product. Pi reverses the product. So next it is remaining to prove that pi preserves identity mapping. So right, pi preserves identity mapping. Pi preserves identity mapping. This is the last condition of our theorem. So right, now let us take to prove this I star identity operator, I star f of x, this equals to f of I of x. This is nothing but f of I of x. This is nothing but f of x, because I of x is equals to x. F of x is nothing but I of f of x. I of f of x. Therefore, I star f is equals to if. I star f is equals to if. This condition shows as I star is equals to I. I star is equals to I means pi of I is equals to I star is equals to I. Therefore, pi preserves the identity mapping. Pi preserves the identity mapping. This completes the proof of our theorem, hence proved. You see, in the statement you have elaborated statement, we prove everything. What is in the statement? We prove everything. So one of the application of Hahn-Banach theorem. Go through with the theorem. Keep learning. Wish you all the best.